French is not at all good. So she did her PhD from IISER Kolkata in 2021, and she works in theoretical quantum information and computation. So I hand over to Shreya to give her talk. All the best.
Thank you for the kind introduction. And without further ado, I'll just share my screen. Yeah. So I think controls are okay. Can you see my screen? Can anybody let me know?
You raised a hand?
Yeah, thank you. So I am Shreya. I used to be from IISER Kolkata. Now I'm at University of Sherbrooke. And today I will talk about user level optimization on intermediate scale noisy devices, quantum devices. Okay. So many of you are familiar with this term, NISQ. It means noisy intermediate scale quantum computers, where noisy means prone to errors, and the term intermediate scale means with fewer number of qubits. For now, the term intermediate scale means up to a few hundred of qubits, maybe 500 or 1,000. But more than that is not intermediate scale, that is a vision for future. Now, why do we need to optimize while using a quantum computer, especially the noisy intermediate scale quantum computer? This is a short motivation kind of thing. So this is one of my circuits that I have implemented on the famous IBM quantum computers. It's not, the circuit is not of much depth. As you can see, there are only, I think 10 layers maybe. But still, you can see the difference between the simulator output and the actual device output. And these four clubbed high outputs or probabilities, the output states that are there is not at all similar to the simulator outputs here. And it's totally a chaos. It's utterly chaotic. The result is utterly chaotic for such a small depth circuit. And this is something that we researchers that work closely with the IBM devices, at least, we see on a daily basis. Most of us don't even use the actual devices, actual quantum devices, and settle with the simulator, say that this is a proof of concept kind of thing and move on. But if we want to use the quantum computers on a, I would say, daily basis, at least for research purposes, the actual devices, we need to do some kind of optimization beyond that is given with these computers itself. So before going into that, I'll give you a bird's eye view of a workflow of a quantum computer. The first thing is to design a quantum algorithm. That is a theoretician's job. Most of us, or maybe all of us, I don't know, do these things. So once you have a problem, you design a quantum algorithm with basic quantum concepts. And then, at least in case of the gate-based models, gate-based quantum computing models, which is also one example of that is IBM quantum computers, you have to design a reversible circuit. Reversible because quantum computing is reversible. And then you need to decompose that circuit in terms of the particular hardware you are going to use, but on a user level. So when I say user level, what I mean is that the physical hardware has multiple layers, and the first layer that we can see and we use usually is the user level. The gates there, that the gates we see there, such as the C0 gate, the CX gate, CR gate, control rotation gate, or the controlled Z gate, or maybe the single qubit gates even. Those are not the gates that the actual hardware implements. The actual hardware implements some pulses uh, that is designed according to the gate that you instruct the computer to use. So that is the logical circuit decomposition. Whatever the user gate set is of the particular computer that you want to use, you need to decompose your higher level quantum algorithm in terms of those gates. And then you need to do a circuit mapping according to the connectivity, qubit connectivity of your device, the device that you want to use. And then the device, what happens usually is the platform that you are using, they decompose your user level circuit into a physical circuit. So this term native gates comes in at that point. So the native gates are the gates that is actually implemented on the physical device. So this is QASM is the quantum assembly language. The logical QASM is the user level circuit, and the physical QASM is the circuit that is that the platform outputs once you input your circuit. So after that, the whole the native gate, the circuit in terms of the native gates is sent to the hardware, and the hardware implements your algorithm and gives you the output. So today I'm going to talk about how you can modify your circuit after you design the algorithm. When you write your circuit in terms of the software visible gates, the software visible gates are the user gate set. How you can optimize that part so that your results are at least a little bit better. Okay, so this is also a bird's eye view of the hybrid classical quantum computer. This is the same architecture that I told in the previous slide. You design a quantum algorithm according to your problem, then you design the logical QASM, the logical quantum circuit, and then there is a quantum instruction set architecture that is unique to the particular platform that are using, not the hardware. And then there is a micro architecture of the individual hardwares. And finally, there is the quantum chip that outputs your circuit, that implements your circuit and gives you back an output. Okay, so why this is hybrid? This is hybrid because as the people that uses IBM quantum computer can relate to this. When you design the circuit, you use your own computer, which is a classical computer. When you design the circuit on a user level, and you send it to the IBM cloud maybe, and then they use it, and the quantum part, the implementation of the quantum circuit occurs there. So there is a host CPU, which is in this case your own computer, and then there is a quantum CPU, quantum control unit, QCU, that implements your circuit. And then there is a physical execution layer. The physical execution layer is the part where they use pulses, and they actually the quantum thingy happens. And then there is a measurement unit. Of course, it measures and gives back into the classical terms. And then there is an interface which gives you back the result. And apart from all this, there is a quantum chip, which is again the physical execution layer, and the quantum chip is kind of similar. And quantum chip is the one that is the only quantum part here. Everything else happens either on a thought level or on a classical computer. This is an example, it's a bit old, it's last year's example. This is an example of what native and software visible gates are. I have 3 examples here. There are 2 superconducting computers, IBM Q and Rigetti, and there is one Traptan. There are software visible gates. I don't think that IBM Q uses U1, U2, U3 these days. They only uses U, which is the U3 gates. And there is only one 2-qubit gate that is C0 in this case. And in Rigetti, there are a different kind of software visible gates and a different kind of 2-qubit gate. And for the Traptan, again, there is a different kind of 1-qubit software visible gate and a different kind of 2-qubit software visible gates. These are the gates that we use when we design a quantum algorithm and implement it, quote unquote, implement it on the quantum computer. These are the gates that we use to build our circuit. And the native gates here are the gates that is being implemented on the quantum level on their devices, the actual hardwares. And you can see these are pretty different from the software visible gates. So there is a mapping there that occurs in between that transforms the single qubit gates in terms of the single qubit software visible gates, in terms of the native gates, and the same for the 2-qubit gates. Now, the optimization part, what can we do? If you remember this figure, this is pretty chaotic, and this is not at all the result one expects from the quantum computers to give, because then it will be useless. So what can we do? This is something that probably most of you know. This is a control gate. This is the matrix of the control gate, and this is what it does. And I won't go into this. But these control NOT gates are the 2-qubit gates, and these gates are the primary sources of errors. If you go into the IBM website and check for the errors of the individual gates, usually you see that the 2-qubit gates are the major sources of error in case of, at least in case of the gate-based errors. So in a circuit like this, the one that I have, there are tuffles. There are 4 tuffles and 2 C0s. One tuffle, to implement one tuffle, you need, this thing changes every year, but I think the standard is 6 or 8. So for one tuffle, you need 6 C0s. And for 4 tuffles, you need 24 C0s, and there are 2 other C0s there, 2 other 2-qubit gates there. So there are 30 C0s there. And one or 2 devices that have like 70% fidelity for a control NOT gate, and these things multiplies. So there are 30 C0s, and each of them has an error of 30%, and that thing accumulates and gives you a crappy result. So today I'm gonna talk about what can we do to reduce this C0 errors, at least. Not the gate-based error, that we cannot do. That is something the people that develop the hardware, they can do. But we can design our circuits in a way, the software visible circuits in a way that these errors, at least the final error, reduce a little bit. So this is called device-dependent optimizations. And the famous problem in this domain is the qubit mapping problem. So this is a qubit connectivity graph of IBM QIQT. Again, if you go into the IBM website and look for the architectures or the connectivity graphs for different devices, you'll see figures like this. So this is a 5-qubit gates, and the connections are pretty simple. You can see just if everyone is connected to the nearest neighbor of there, and there are devices that has multiple connectivity. So the 0 can be connected with 1 and 2 like that. But for this case, the case that we are going to study today is there is a linear connectivity. 0 is connected to 1 and 1 is only connected to 0 and 2. So how do you implement a C0 between 0 and 3? People that uses the people that uses the naive software level thing, what you do in your code, this is for the children, the people that are getting introduced to this field, not for the experts. So what you do in your code that you write a C0 and you put the 0 and 3 in your bracket. I think that's it. And then the C0 occurs. But what actually happens there? Because there is no connectivity, no 2-qubit connectivity between 0 and 3. So you have to go through 1 and 2. And how do you do that? You use swap gates. What does the swap gate do? The swap gate swaps the qubit. So if you implement a swap between 0 and 1, at the second step, whatever quantum state were mounted on the qubit 0 comes down to qubit 1, and vice versa. Whatever quantum state was on qubit 1 goes back to qubit 0. And to implement a swap gate, you need again 3 C0s. So, yeah. So if you want to implement a C0 between 0 and 2, you need to swap the qubits 0 and 1. So you have to swap the state. You have to mount the state that is on qubit 0 to qubit 1, so that virtually or logically there is a C0 now between 0 and 2. Then you implement the actual C0. You instruct your circuit to perform a C0 between 1 and 2, and the final result is there is a C0 now between 0 and 2. So number of swaps needed to implement a C0 between 0 and 2 is 1, I think. Yeah, 0 and 1, there is a swap. This is wrong. And in order to do a swap, you need to do 3 C0s. Like I said, there are some devices which has like 30% error in one C0 case. So when there are C0s in your own circuit, and the circuit I showed with a depth of 10, it had 30 C0s already. And if I want to do the swaps, and let's say out of those 30 C0s, you need to swap at least 5 of them. So if you want to swap at least 5 of them, there is a cost of like 15 C0s, and there were already 30 C0s. So finally, what you have is a 45 C0 cost. So the cost gets multiplied, the error gets multiplied again. This is an example. So this is a circuit that I want to implement. There is a C0 between 0 and 2. And there is a C0. The first C0 is between 0 and 1. This is the software visible circuit. These are the X's. The first layer is the X's. There is a swap. There is a C0 between 0 and 1. This is the C0 between 0 and 1. And there is another C0 between 0 and 2. And as you can see, to implement this one C0, I have to implement 4 C0s. Now, what can we do so that we can change these things? The first thing that we can do is we can optimize through qubit allocation. So what is qubit allocation? So there are, when you think about it, what do you have in your hardware? You have 5 qubits, and all of them are initiated on the 0 state. I am talking about IBM here. It might be different for different platforms. So what you have is 5 qubits all initiated in their ground state, and you can change them as you want. So nobody is stopping you from assigning the logical qubit 0. The logical qubit is the qubit that is in your circuit, the circuit that you made from your quantum algorithm. So you can assign your logical qubit 0 to a physical qubit that has the number 5. That is qubit allocation. So in this case, what is the allocation? In this case, I have allocated logical, this circuit is the circuit on the left is the logical circuit, and the circuit on the right, for now you can think of it as the physical circuit, though it's not the physical circuit in reality, but for this small example, you can think the circuit on the right as the physical circuit. So here the assignment is qubit, logical qubit 0 to physical qubit 0, logical qubit 1 to physical qubit 1, and logical qubit 2 to physical qubit 2. But the architecture of IBM-Q Athens, for the architecture of IBM-Q Athens, this allocation is not good. As you can see, for implementing 2 CNOTs, we have to implement like 5 CNOTs. So this is not good. So what can we do? We can allocate our logical qubits in a different way on the physical hardware by looking at the qubit connectivity graph. What have I done here? I have allocated 0 to 1 and 1 to 0 and 2 to 2. By doing this simple allocation, I have reduced the cost for 3 CNOTs. And if I assume that the error for 1 CNOT is 30, you can see how much cost I have saved here. So this is something that the IBM-Q optimization level 3 does. So when you write your code and when you send it to the hardware, you can assign what optimization level you can use. So there is 0, there is 1, there is 2, and there is 3. And frankly, I don't know what each of these level actually ensures. I have played with it a bit, and I have figured out that this allocation doesn't happen in level 0. Level 1 and 2, for level 1 and 2, it rarely occurs, but for level 3, the inbuilt optimization of IBM-Q does this allocation. They allocate the qubits, the logical qubits to the physical qubits in a way that it gives you a better result. But it's not optimal. The circuit that I have shown you at the beginning with the crappy result, this circuit, here I had used IBM-Q optimization level 3. So people have played with this optimization of this allocation problem or the qubit mapping problem a lot. And there are few ways that you can improve your logical code, improve your user level code, get better results. So to find a suitable mapping, what you can do, you can look at the initial mapping transition. What do I mean by that? What do I mean by that is you can look at the mapping itself, the mapping of the device that you want to use. First, you find out what are the parameters there, what are the errors there, and choose the best possible device that is given to you, the one with the least gate errors, the one with the least connectivity errors. And then what you can do is you can assign your qubits on a user level. You can allocate your qubits on a user level. You do this transition. You don't depend on the IBM optimization level. You do this transition. But this is a very small circuit. And that is the problem. This is a very small circuit. And when you have a circuit with a depth of, let's say 50, and there are like hundreds of CNOTs, you cannot assign those qubits. You cannot assign those qubits by thinking of every one of the CNOTs. What you can do, you can identify your initial layer of CNOTs, and then you can implement, you can assign a mapping from the logical qubits to the physical qubits. that is entitled to give you a better outcome. So this finding out this initial mapping is a problem that we define as qubit mapping problem.
Okay, Shreya, you have less than 5 minutes.
Yeah, I can wrap that up.
Okay,
yeah.
Thank you.
So, okay, so these are the matrix. These are metrics that you look at when you figure out how to do the qubit allocation. One is fidelity. Fidelity is what your output should be, and is a metric that that gives you the outcome that what your output should be and what your output you are getting. And there is also parallelism. What your circuit can do is you can identify the C nodes that are independent of each other and you can assign those parallelly. And there is also scalability, but the scalability problem is not a problem for NISQ devices because these computers has like hundreds of qubits. The scalability will be a problem when we'll have more than that. So this is an example of the parallel scheduling. There are two CNOTs that are independent of each other and I can schedule them at the same time. So there are solutions to this problem. One is exact solution approach, but this we can only use if my logical circuit is like very small. And there is a heuristic search. You can define a cost function based on the matrix that I've shown you. And that cost function will give you a result, an outcome which you want to reduce. So that is called a heuristic search. You can initiate a search within of mappings, of initial mappings, and get the result which gives you the lowest cost, and that is your initial mapping. You can start with that mapping. There are further optimizations like crosstalk mitigation, and I won't go into that because of time. And also, but one little trick I want to say that is use the virtual Z-gate. The Z-gate, and at least on IBM quantum computer, the Z-gate is virtual. There is no cost of a Z-gate, the Z-gate. And if you can design your circuit in a way that uses more Z-gates than X-gates, you can get a better result. There is also readout errors. So one quick fix for the readout errors is you can initiate your circuit in 0 and you can initiate your circuit on 1 and then you can take the average of the two. Of course, you have to reverse your circuit for that, but that's easy. Just before measurement, put another layer of X gates. So there are some existing solutions for circuit optimization. There is Streak that is open source. I don't know if Stack is open source, and there is also QIQT. There are the references. These are software packages that does these things for you, and these have proven that they get better results from the platform-based results. And thank you for listening to me today.
Okay, thank you, Shreya, for the nice talk. I could see a few questions in the chat. Like people are asking certain questions. So would you like to ask one or two questions, like very quickly?
Yeah, sure.
Yeah. Anybody? Like I could see some 4 or 5 questions in the chat. So yeah, because we don't want to read off questions from the chat because there are too many of them. And to save time, maybe later on, if somebody wants to answer, they can type in the chat perhaps. But if somebody wants to answer from the speaker directly, you can speak up now. That's better. So no one? Okay. So then we thank the speaker again for the nice and compact talk. And I think she will be free to answer your questions later on if needed.
Yes,
so
any of you
okay.
you want to ask, you can mail me or text me if you have my number. So it's fine.
Okay, thank you, Shreya, again. So now we will move to the next talk, and the next talk will be by Siddhartha Patra. Is he here, Siddhartha?
Yes, I am.
Okay.
Can you hear me?
Yes, clearly. So Siddhartha is a PhD. you are a PhD student in IISER Kolkata right now?
Yeah, just submitted thesis.
Oh, great, great. All the best. So he works in condensed matter physics, I guess, in
Yes.
Professor Lal's group, right?
Right.
Okay, okay. Welcome to the session today, and please take over your talk.
Yeah, can you see this screen?
Yes, we can.
Yeah. So thank you for giving me this opportunity to talk about my research. Today I will talk about topological entanglement entropy, which is a special property of a topologically ordered system, and how it is related to a graph polynomial. We will discuss that. Before we start, we start with a brief introduction with a Landau-Ginzburg-Wilson paradigm. So, in condensed matter theory, understanding phases and phase transitions is a very important task because there are many phases and phase transitions. So, one framework was needed to describe those phases and phase transitions or characterize them. So, Landau, followed by Ginzburg-Landau in 1950, a paradigm was established which is called Landau-Ginzburg-Wilson paradigm. Wilson brought the renormalization angle in this framework. It was understood that phases and phase transitions can be understood via the breaking of some symmetry, and each phases can be associated with some local order parameter. By tracking that local order parameter, you can track the phase transition. That was the idea. Some examples of phase transitions are normal phase to superfluid transition, paramagnetic to ferromagnetic transition, etc. Now, recently, recent means a few decades, some phases like spin liquids, fractional quantum Hall effects, and spin superfluid to insulator transitions. Some phases shows that only symmetry is not sufficient to characterize those phase transitions. So some new paradigm is required to uh, to describe these new classes of phases and phase transitions. Quantum order, topological order, some examples or some framework to describe such phases. Quantum order is more general framework. Topological order is special part of that quantum order. I will mainly focus on the topological order here. What are the special properties of this topological ordered phase? So the phases of the systems comes under this topologically ordered class has these special properties that the ground state degeneracy is very robust against any local perturbations, and its excitation shows fractional statistics. It has gapless edge states, and long range entanglement entropy is also an important property of these phases. Unlike the Landau-Ginzburg-Wilson paradigm, these phases shows the lack of local order parameter. Instead, they shows non-local order parameter like Wilson loops, operators, etc. Some examples of these phases are toric code and fractional quantum Hall states. To give an example, this is the simplest topologically ordered Hamiltonian, which is described by Z2 lattice gauge theory, Hamiltonian. In the Hamiltonian, you can see it is made out of two terms, first term and second term. The second term, when the second term dominates, you can see the second term is made out of non-local operators. This non-local operators forms a plaquettes as shown in the figure right side. Plaquette means the smallest closed objects that you can form in the lattice. The spins residing on the links of the lattice forms that plaquettes. Now, when the second term of the Hamiltonian dominates, then this kind of plaquettes or closed loop-like non-local objects gets activated, which are called string loops. And in the strong T limit, when the second term dominates, this kind of objects, loop-like object of all sizes dominates, which is called stringnet condensed phase. This is a liquid phase of this kind of closed loop-like objects. As you can see in the left, when T is small, then there are very few closed loop-like objects. But when T dominates, the entire system is filled with the string loop-like object or string nets, which is called. A special class of topologically ordered phase is described by Z2 Guess theory, which shows a special class of string net condensate, which is a string loops. That means loops of all sizes, non-intersecting loops of all sizes exist in such phases. Now, the entanglement signatures, studying entanglement signatures of such phases is very important task. Such phases shows a very different entanglement properties. They shows area law, but along with the area law, there is a geometry independent piece. So let's say this square box shows the system, the topologically ordered system. If you take the subsystem A, in general, the entanglement of it will depend on the geometry of the subsystem. That is the first term, alpha LA. LA is the area of the perimeter of the region A, and gamma is the geometry independent piece in the entanglement measure. That is very specific to this topologically ordered system. The structure of this gamma is like this, as shown: number of disconnected boundary times log D, where D is the ground state degeneracy of the system. So this is the structure of the von Neumann entanglement of such phases. That means if you take the subsystem as shown in the left figure, there is no hole, so the number of disconnected boundaries is 1. So gamma will be simply 1 times log D. In the right figure, as you can see, you have punctured a hole, so the number of disconnected boundary is 2. That means the number of NC is 2. That means the gamma will be 2 times log D. So that's how this entanglement of it depends on the topology of the subsystem you choose. To answer the question that what is the entanglement structure, tripartite information was computed in 2006 by Levinson and QIQT. It was shown that if you arrange 3 subsystems A, B, C in an annular form, and you calculate the tripartite information, you get non-zero value, and which is dependent on the topological entanglement of the S topo, which is nothing but log D. This non-zero tripartite information shows the non-local structure of the correlation in this topologically ordered system. Though tripartite information was shown, but it was also not clear that what is the dependence of this tripartite information on the arrangement of the subsystems. So we calculated the same tripartite information on a different arrangement for a linear arrangement of ABC, where I have opened up or I cutted the arrangement of subsystems. In that case, we see that tripartite information vanishes, which shows the very sensitive dependence of tripartite information on the collection of subsystems or the arrangement of subsystems. So what are the questions? The questions is, the tripartite information was known, what is the general multipartite entanglement structure of such topologically ordered system? How the topology of collection of subsystems affect or intervenes the multipartite information measure? And third, what is the general multipartite irreducible correlation structure of such topologically ordered system? To answer that, we generalized the tripartite information definition, which is already known, to higher n-partite information. The tripartite information is the alternate sum of higher number of subsystem entropies, as you can see, as shown here. Similarly, four-partite information is also a similar way. You can extrapolate. we will calculate this. So before we calculate this, we mapped this problem of multipartite information to a graph problem. Before we go to the graph problem, let's discuss what are the special properties of this multipartite information. For this special entanglement structure, this SA is equal to alpha L minus gamma A. This special structure, alpha L is the area law term, or gamma is the constant correction to the area law. For this special structure, this IN shows that all geometry dependence, that means all perimeter dependence term vanishes. Only IN depends on the gamma, the last factor. That means the topological entanglement of the part. This even in general, this multipartite information will cancel any volume terms also, though that is not our case. By mapping the collection of subsystem, we mean, let's say in the left figure A, there is a complicated collection of subsystems. We create a corresponding graph gamma. How? We replace each subsystems by a vertex and nearest neighbor connections of two subsystems with an edge between those two subsystems. Thus, we create a corresponding graph. Now, we have shown that this multipartite, n-partite information is proportional to a graph polynomial beta gamma at a particular value -1 times S topo, the topological entanglement. Now, what is beta gamma? So this is the important part. What is the graph polynomial? We'll describe this shortly. Graph polynomial is a special quantity for a particular graph gamma. X is a variable. Now, let's say for a graph gamma with n vertices, the polynomial is defined like this, up to n-1th order. So it is an n-1 order polynomial. Individual DNIs captures the subgraph topology of all induced subgraphs of gamma with I vertices. Now these quantities, this polynomial value depends upon the embedding. So if you can embed the graph on higher genus surfaces, as you can see as shown here, for non-planar embedding. But in our case, we will focus mainly on planar embedding. So for a cycle graph, that means a circular graph here with 4 vertices, the polynomial value is given here. So let's say we want to calculate D4 2. 4 means there are 4 vertices in the graph, and 2 means we want to calculate the polynomial value for all subgraphs with 2 vertices. Now there are 4 vertices in the main graph, so there are 4 C2, that means 6 possible induced subgraphs. So in the subgraphs you can see all 4 possible subgraphs. In the top row, they are forming one connected component, so they are shown by one number. In the bottom row, they are formed by 2 disjoint islands, so we are counting as 2, so the total number is 8. So that's how we count for planar embedding. For higher embedding, it will be more complicated. Next, using that graph polynomial, we have shown that for any arbitrary number n arranged in an annular form, the n-partite information is nothing but proportional to chi, the Euler characteristics of that cycle graph embedded on a planar manifold, that is 2 times S topo, or the topological entanglement of it. That means the n-partite information is independent of n and depends only on the topological numbers, 2 topological numbers. One is Euler characteristics and another is the topological entanglement of itself. Next, as we have shown that this multipartite information is highly sensitive to the deformation of the subsystem. So our goal was to show the transformation under which this is robust. So we have shown that if you add nearest neighbor handles in the collection of subsystems, then the multiparty information does not changes. It remains same. Even if you create punctures holes inside a subsystem or had self loops in the subsystem, then also the multiparty information remains invariant. So this shows the robustness of this multiparty information for such topologically ordered phases. Next, we show the deformation that trivializes the multiparty information. As you can see, if you cut the annular thing and create a linear form, then the multiparty information vanishes. If you isolate an subsystem, then also vanishes. And if you add an appendage to this, then also the multiparty information vanishes. Note here, though the NIN, that means n partite information vanishes, n-1 partite information will be non-zero for this annular arrangement formed by n-1 number of subsystems. Another important result is that, as we have showed, that if you add nearest neighbor handles, there is no change in the multiparty information. But if you put more than nearest neighbor handles, the multiparty information again trivializes. But in that case, two smaller annular arrangement gets created. For such smaller arrangement, you again get non-zero multiparty information. Apart from this multiparty information, we also calculated correlations. So we saw that k-partite irreducible correlation, which is a measure of correlation present in the k-particle reduced density matrix, but not in any lower particle reduced density matrix, which shows that the n-partite irreducible correlation is upper bounded by the n-partite information, that is non-zero. In this way, we have also shown that we know that strong subadditivity for three subsystems is known for von Neumann entanglement of it. We could derive a general n-partite general strong subadditivity for n subsystems for such topologically ordered system arranged in an annular form, which is given in the point 2. This non-zero upper bound shows the presence of non-trivial irreducible correlation in such topologically ordered system. Now, we have already shown that for an open arrangement, the multiparty information vanishes. That means the upper bound vanishes, so the irreducible correlation is also zero for such open arrangement, which shows the importance of closed loop-like objects. Thus, we conclude my results. So for any n greater than 2 number of subsystems arranged in a closed loop of any sizes in the system are strongly entangled with each other with n-party irreducible correlation and n-party irreducible entanglement. Sorry, n-partite information. This shows that in the ground state of topologically ordered system, closed loop-like objects are formed, which agrees with the string loop condensed phase of topologically ordered system. So this is a quantum information theoretic way of showing the presence of string loop condensation in a topologically ordered system. Now, what can we do further with this thing? We have only used the planar embedding of this graph to derive the topological entanglement of it. We have already generalized in another work, as can be shown in the archive work, where we have generalized this for higher genus manifold, which can be used to describe higher dimensional topologically ordered systems, and which has further application in topological error correction. Another important thing is using the higher dimensional graph model, we have actually derived or shown the emergence of Euler characteristics in very general setting. So I would like to thank Dhruv Basing, Kainika ma'am, and Momonti ma'am, and Somo sir. I would like to thank CSR ISA Kolkata for the funding during which I did the work. These are the references. Thank you.
Okay, thank you, Siddharth, for the nice talk. It was really informative. So anyone with a question? I see a hands raised. Yes, please speak up. If anybody has any question, please, you're free to ask. Please continue. Actually, we have enough time for questions, and I saw people were asking in the chats. So there's a chat here. Yes, please unmute and please ask questions. Okay, may I ask you a very simple questions like Siddharth?
Yeah.
So the phase transitions you encounter, so which order phase transitions are these?
Oh, so this we are not talking about here any phase transitions. We are talking about a particular phases, which is a topologically ordered phases.
Yes, but if you encounter phase transitions there, so
Okay.
can you specify an order there?
Actually, you cannot use the standard order parameter here.
Okay.
So can you define the phase transition order then using the derivative of the free energy?
Yes, usually we do that. So can you quantify free energy term for these kind of phase transitions and all?
No.
Okay.
The model I gave here, so I cannot give you the, so I can say maybe higher order, more than 2 or continuous phase transition.
Okay.
But I don't know any construction of free energy for this kind of phases.
Okay, I understand. Because okay, that's fine.
Because the Hamiltonians are written in terms of non-local operators, so the free energies are written in terms of local
yes, exactly.
parameters, I think.
You should
So
be able to define a differentiation.
Hard.
Yeah,
yes,
it is. So nobody has done it till now for these systems, like tried to do it. I'm asking. So nobody has done it. Have you seen somewhere?
I have not searched, or okay. I am not aware of this. I will search about it.
Okay. Thank you. Anyhow, so we actually
people have computed entanglement spectrum and entanglement entropy for these kind of things.
Okay, I understand. So yeah, so you so people. So mostly in terms of entanglement entropy and all, people want to understand. Okay, that's clear. So because we are left with another 6 minutes actually, so if anybody has any question, please speak up. We have time for that. But if not, yeah, Suvayan has a hands up. You want to ask something, Suvayan?
If we have time, to just sort of summarize results and just set up like what is the relevance of this in the big context? Like, do you have any big picture ideas like about the research program?
So what I will say, the understanding the entanglement structure of this topologically ordered system is very important in the application point of view also, like to construct a error correcting topological quantum circuit or quantum computer. If you understand the entanglement structure, That would be very helpful, as we have shown that these multipartite informations are robust against certain deformation. So you can harness these properties. Because this was unknown so far. So using these results, you can create such devices in such a way that you can harness this robustness.
So are you saying that like under some physical transformations, your state won't change? Like are you finding invariants of sorts?
Yes. So you can map this addition of nearest neighbor handles and addition of self loops to some physical models. Then what kind of model changes does these things? So under those model changes, it will be the entanglement structure will be invariant. So this gives an extra security on top of. So already this topological order system is only is robust against any local perturbation. So there is already a safety, but this extra entanglement robustness is giving another level of safety.
Okay, maybe a slightly more technical question. You're saying that under local perturbations, your entanglement measure is, the entanglement entropy is invariant.
Ground state properties are invariant, so the entanglement will also be.
Oh, so under local perturbations, ground state properties are invariant. So if I sort of
Ground state degeneration, I mean. So yes.
okay, thanks.
Okay, so is there any more questions? So if not, we can thank the speaker. Thank you,
Thank you
Siddharth.
for inviting me. Thank you.
Yes, thank you very much. So we can move to the next talk. It can be a little bit, some 2-3 minutes early, but if Ms. Ramita Sarkar is available.
I am here.
Okay, yes, hello. So so are you ready to give the talk?
Yes, I am ready to give.
Okay, so we can start the next talk. So we'll have now Ramita Sarkar, who is an SRF in IISER Kolkata right now and working in quantum information. So I'll hand over to her for the talk. Thank you.
Thank you for kind introduction, and thank you for inviting me to speak here. I am from IISER Kolkata. I am Ramita. I am working under Professor Panigrahi. Today I am giving my talk on quantum hypergraph state. Is this workable?
Yes, we can see your screen clearly.
Okay.
Yeah.
I am today I will talk about hypergraph and graph state, and from construction of graph and hypergraph state from the consecutive mathematical graph and hypergraph, and some relevant definitions regarding this. And after that, I will proceed for the multipartite quantum entanglement for hypergraph state. After that, squeezing and coherences and non-classicality criteria like Mendel's Q parameter, higher order anti-branching, Agarwal-Tara, and so on. First, I define what is graph. Graph is a pair of set in which X is a set of vertices and E is a set of pair of vertices.
I think your audio is breaking up a little bit.
Okay.
Yeah, please adjust.
One second, I am trying.
Okay. So it seems we have a small technical glitch or something. I'm not sure, but let's wait for a little bit.
I am joining from Shreya Banerjee's account.
Okay.
Sorry for the delay.
Okay. That's okay.
Am I audible right
Please.
now?
Yes, very much.
Hello?
Yes, please.
Hello?
Start. Yes, can you hear me? Hello. You are audible.
সাউন্ড আমি কিছু শুনতে পাচ্ছি না আনমিউট করা
We can all hear you clearly.
হেডফোনটা লাগবে না Sorry for the delay. I am starting from the beginning.
Yeah, sure. Please.
I am going to discuss about hypergraph and hypergraph state. And from the very beginning, we are discussing about graph. After that, construction of hypergraph from mathematical hypergraph and generalized concurrence. After that, we'll come to the multipartite quantum entanglement for hypergraph state.
Miss Ramita, can you make it
squeezing and coherence is another criteria like non-classicality criteria, Mendel-Q parameter, higher order anti-bunching, Agarwal-Tara criteria, and so on. Firstly, we define graph. Graph is a pair of sets in which X is the set of vertices and A is the set of pair of vertices, that is the edge set, that is its element are itself edge. Like here I have given one example of graph that is Shreya di full screen করতে পারছি না এটার এখান থেকে আর ফুল হবে কি And here I have taken or as an example of 5 vertices state, that is here we see here number of vertices are 5, that is x1 x2 up to x5, and number of edges we here in this graph is 6, like e1 e2 e3 e4 e5 e6 up to e6, and e1 itself is a set of 2 vertices like x1 x2 and x2 x3 e2 consists of x2 x3 and so on, and such as E is consist of set, that is why it is called a family. After that, I will come to hypergraph. Hypergraph is a generalization of graph which can connect any number of vertices. That is, here we have seen that here number of vertices is like 7, and in one edge we can connect 4 number of vertices, here 2, here 3, and also here also 1. In graph, typically the length of the edge is 2. Here the length can be any number, like if we have an n number system, we can connect n number of vertices and so. Now we will come to some definitions about related to hypergraph. Like here we can say that if 2 vertices are connected by an edge, then they are called adjacent. Like here v1 and v2 are connected in the edge e2, so they are adjacent, and if they are not, they are called disjoint. Like like here v1 and v7 are not connected, so they are disjoint. And adjacent vertices are also sometimes called neighbors, as they are connected through one edge and anything. And loop is an edge containing single vertex. Like here E1 is a loop only containing the vertex B1. And degree of vertex is the number of the all edges containing the vertex X. Here, the degree of the vertex like V2, it is 2. It is already in the edge E2 and E4. That is the degree is 2. Complete K graph is consists of all possible combination of hyperedges of length K. If we consider a complete 2 graph, it will combination of all possible combination of of edges length 2. And typically cluster state can be told as a graph state, and as graph is itself is a subset of hypergraph, the cluster state can be defined as a hypergraph state 2. And now we will come to the some applications like hypergraph and is very much applicable in chemical hypergraph theory and telecommunication, networking, data structure, image processing, artificial intelligence, and so on. Also, people are using hypergraph state in quantum information and algorithm too. After that, we will come to the full screen पे ये होएगा छे তোমারটা খুলে গেছে কত চালাচ্ছে Am I audible? After that, we'll come to
You are
the
audible.
formation of
Yes.
hypergraph state from mathematical hypergraph. Here we have taken a 4 vertices hypergraph. That is, it consists of 3 edges. One edge is of length 2 edges of length 3, and one edge is of length 2. That is, we see 1 and 4 connected, 1, 3, 4 connected by another edge, and 2, 3, 4 is connected by another edge. And we also made the connection based on the edge connection. Here, like 1 and 4 is connected, so that we make a control and Z, and we can also use Z in 1 and control in the 4 position, and for 2, 3, 4 to control another Z, and 1, 3, 4 to control in 1 and 3 and Z in 4. And this is how we can construct from mathematical hypergraph to hypergraph state. Like, here we take the state psi. Here control Z for 1, 4, as this is only 2 length 2 edge, that is why 1 control. This is of length 3, that is why 2 control Z. Another similarly 2 control Z. And also we can simplifying it will turn into this state. And also we can write in the matrix format or decimal format, like this is 0, this is 1. We can also write this in this format too. And now we will come to concurrence. Concurrence is a very important measure, first coined by Hill and Wouters in their physical review letter paper 1997. It is possible for entangled state, and it is vanishing for all separable state. If we consider in particle system if we label the particles as A, 1 up to n, and we consider a pure state, and the density matrix will be the outer product of the state psi. And if we consider the m particle whose bipartite separability is we want to develop or discuss, and m should be less than n, that is total number of the particles. Then the generalized concurrence em for the bipartition m prime will be this. This is developed by Bhaskar and Panigrai in their 2017 paper. And also this can be written as the area or the based on the wedge product. They can the concurrence can be described as the area 2. This suppose here we take a 2-qubit system, And after that, we will define two vectors, that is chi0a and chi1a. These are the two vectors. If these two vectors are parallel, then they can be told that they are separable. Like if they are parallel, they will not form any area. Then the states are separable. For entanglement, they will cover an area, and this area will be the entangled concurrence. And the concurrence is given by this formula. This is the mode of the wedge product, and sorry, wedge product is the generalization version of cross product. I have to mention this before. And also, this is developed by Banerjee and Quantique in 2020's paper. They developed concurrence as the area under a parallelogram spanned by the post-measurement vectors. If we consider two vectors, like and an area under this parallelogram can be considered as the concurrence of this state. And for multipartite system, we can consider like 3-qubit multipartite system can be considered as the total entanglement can be considered as the sum of the all bipartitions. For 3-qubit system, here we see there are 3 bipartitions, A, BC, BAC, and CAD. Similarly, for 4-qubit also we get in the similar fashion. And for the single cut bipartition, that is ABC, this is the single cut bipartition, and like ABCD, this is 2 cut bipartition, and so on. That cut can be many more depending on the number of qubit. For single cut bipartition is simply true of determinant of root over of determinant of density matrix of the reduced density matrix of the system A. And in this way, we can calculate the 3-qubit state entanglement, that is total entanglement, adding this 3 bipartition A, EB, and AC, that is determinant of rho A, determinant rho B, and determinant rho C. That will come to 3. After that, we will come to the complete 2, 3, 4 graph for invertices system. Complete 2, 3, 4 graph is already I have told, that is complete K graph. Complete K graph means consists of all possible combination of edges, hyper edges of length K. That means complete 2 means all possible combination of edges of length 2. That complete 2 graph is simple graph state. As because the length is 2. Complete 3 similarly of all possible hyper edges of length 3, and complete 4 is of length 4. This is some typical structure. One example of complete 2, complete 3, complete 4 graph for this is for 4-qubit system. This is also for 4-qubit system, and this is for 5-qubit system. I have given an example. And after that, we calculate the lot of concurrences with number of vertices for these complete classes of hypergraphs, like complete 2, 3, and 4 hypergraphs. Complete 2 hypergraph, we see that concurrence is increasing with increase of the number of vertices. Complete 3 similarly similar pattern, and for complete 4 the pattern is same. And if we plot in the log scale, this will come to linear. That means the increase of concurrence with respect to the number of vertices is linear, is exponential. The curve is exponential. The number of with respect to the number of vertices, concurrence is increasing exponentially. And in the similar fashion, we also studied for complete 3, 4 hypergraphs and their concurrences. It will with the same pattern. After that, we calculate for the invertices single edge system. That is, these hypergraphs are having only one edge, that of length n. If invertices system, there will be only one hyper edge of length n. Here I have taken as an example of 5 vertices system, that is of length length 5 and only single edge is there. That is, this is the edge. And it is also depending on the qubit, it is also increasing in the exponential manner. And after that, what we have studied here, that is the maximum concurrences are found for the complete two graph states, and the minimum are found for the single hyperedge, and complete K graph increases exponentially with the number of vertices. After that, we will come to the squeezing. Squeezing is almost like one quantum property can be told as a quantum property. And for that, we have taken a generalized expression of hypergraph. This is G is a generalized hypergraph state for for 2 to the d dimension for in qubit d qubit system means 2 to the d number of d vertices system, and it will go up to 2 to the d. And we have taken creation and annihilation operator as these two matrix, and the corresponding commutation relation for the finite dimensional Hilbert space is not same as the infinite dimensional Hilbert space as we study in our book. This will not come to the I. This will have another part. This is this finite dimensional Hilbert space commutation relation. It was developed in 1992 paper, PRA paper, and rest criteria are same. Like when it act on I, it will give this a act on I root over I minus 1, and a dagger I on the root over I plus 1, I plus 1. And after that, we calculate squeezing for hypergraph state. Firstly, if we take two non-commutating operators or anything quadrature, we if they don't commute, we have the uncertainty relation. And after that, we define the degree of squeezing as AC and SB. If we will say that the state will be squeezed in a domain in a quadrature A or B. If suppose AC will less than 0, then it we can say that this state is squeezed in AC. After that, we take the average or commutation average of hypergraph state of position and momentum operator in the basis of hypergraph state, and we find that position and momentum operator average in the basis of hypergraph state are coming to be 0. So there is no uncertainty in X and P for the hypergraph state. So we shift from position momentum to number and phase, and we show that we see that there are uncertainty relations for hypergraph state. And first we define number operator as n, and we took the average of number operator as in dagger average. This is coming to 2 to the d minus 1 by 2. This here we see that this does not depend on the hypergraph itself, only the number of vertices. If we take a d vertices system or 2 to the d dimensional system, then it will come to this no hypergraph dependency. Similarly, for n square average, it will also not hypergraph dependent, just vertices dependent. And after that, we define the phase and phase state, and we phase operator also. This is a phase operator is already in the literature in 2007 and 2020's paper. And we define phase operator in the number. We expressed the phase operator in the number basis as this. And after that, what we found that P is a Hermitian circulant matrix. And this is the pattern of circulant matrix. This will just rotate, like it will start from C0, C1 up to Cn minus 1, then C0, Cn minus 1, N minus 2, dot C2, C1.
and the diagonal element are same. This diagonal will be the C1, this after that C2. In this way, the element will rotate. After that, we calculate the variance of the phase operator. And after that, we come to the number phase commutation operator. And we also interestingly found the number and phase operator as a skew Hermitian Toplish matrix. Toplish matrix is such a matrix, its element follows this rule: Aij equals to Ai plus 1, J plus 1. That is, this element will be same as this will be same as this, and Ai minus J, they will be same as the Ai minus J. The element, if the I minus J quantity is the same, then the element will be the same. And we found that our commutation operator skew Hermitian Toplish matrix. And then we study that no squeezing can be found for the number with respect to number operator for hypergraph state. Always the operator is saying that the quantity, the degree of squeezing is always greater than 0. We calculate from the maximum and minimum value of the eigenvalues, and we can come to the conclusion that is it is always greater than or equal to 0. And so we can conclude that it will have no hypergraph state will be squeezed in number operator. And hypergraph state are found to be squeezed in phase quadrature. There is a possibility, not always, that all hypergraph states are squeezed in phase quadrature. Some of the hypergraph or hypergraph state can be found to be squeezed in phase quadrature. Like in our example state, what we have given in that previous example state, that is the negative example. That in that case, the hypergraph state is neither squeezed in the number quadrature nor in phase quadrature. And the hypergraph G having D vertices and no hyperedge. Hyperedge means obviously length more than 2, has the -1 as the degree of squeezing in the phase quadrature. Always it will be -1. This is the maximum. Minimum value of squeezing. No squeeze state can cross this value. And hypergraph with number of vertices D greater than 3 and exactly one hyperedge containing all vertices are squeezed in the phase quadrature, and they will decrease asymptotically close to -1. And here I have given an example how this decreases. This decreases. This is a pattern. This is asymptotically decreasing. And after that, we come to the maximum and minimum cases for D1 minus graph. That is, the number of vertices are D, and the length of the edges are D1, D minus 1. And this is, we see the minimum and the maximum cases. Minimum cases follow the decreasing pattern asymptotically, but maximum is not. And this is the summary of what I have told already. That is, hypergraph state has no squeezing in position and momentum, and hypergraph state are not found to be squeezed in number of operators. Some of the states are squeezed in phase quadrature. Some of them, some of the classes of hypergraph has the minimum squeezing in phase quadrature, and some of them are following some patterns. After that, we come to the coherences. Coherence can be defined as a two kind of
Miss Ramita, can you hear me?
Found in the literature.
Hello?
Among them is one relative entropy of coherence. This is the
Ramita, can you hear me? Hello?
Subtraction of the von Neumann entropy of diagonal matrix of the density matrix from the diagonal matrix. From the density matrix. And von Neumann entropy
I think she cannot.
Rho log rho. But we have found that von Neumann entropy, that is the relative entropy coherence for hypergraph state, will increase linearly with the number of vertices. Hello?
Can you hear us?
फिर से
Ramita?
नहीं सुन नहीं पा रहे हो?
It's not clear.
मैं भी कुछ नहीं सुन रहा. तो क्या करूँ? Actually, do one thing. Use a chat box kind of thing. Chat में कुछ लिख लो. मुझे नहीं पता क्या हो रहा है. Explain. Hello.
Hello.
Hello. Are you getting?
Can you hear us?
Yes. Right now
Okay,
I can hear.
okay. So I just wanted to tell you that you can take maybe some 3-4 minutes if possible.
Okay.
Please.
Okay. This is relative. This will increase linearly as because we get the.
Sorry, we don't see your screen either. It's I think the Shreya's presentation, which is we can see now.
Now can you see?
No, yeah, we can see now. Yes.
Okay. So this is the cause of the linear increase is the cause we have calculated theoretically that is the relative entropy of concurrences is d log 2. That is why we get the linear pattern. And also we check relative entropy of coherence in the phase basis. In that case, we get the maximum and minimum, not any kind of typical behavior is found. And after the L1 norm, and also we get the relation for in the number basis, that is 2 to the power d minus 1. And for L1 norm of coherence in phase basis, there is no like any condition can be found that is maximum and minimum kind of thing. The maximum and minimum kind of thing is found are found. No typical behavior is found like any relation like this kind of relation has been found. And this is the states which have the maximum coherences, that is the length of 4 for D5, length of 3 for D4, and length of 5 for D6. And this is the summary. Summary means I already have told. And we have, after that, we found the non-classicality criteria. First one is the Mendel Q parameter. And we cannot check Mendel Q parameter using Mendel Q parameter, the non-classicality of hypergraph state, that as it is 0, greater than 0 for in greater than equal to 3. After that, we checked for the higher order anti-bunching. If this quantum state is told to be lth order anti-bunched if DL is less than 0, and we found that any no hypergraph state is found to be lth order anti-bunched. So we move to the Agarwal-Tara criteria, and in the Agarwal-Tara criteria, we found that can be using Agarwal-Tara criteria only, the non-classicality of hypergraph state can be determined. And this is the typical results. That's it, and thank you.
Okay, thank you, Ramita, for the talk. And yeah, we are sorry that there were lots of technical glitches, so you lost a lot of time. So you had to rush. So is there any questions? We can take a few quick questions. Okay, if there is none, then I ask the participants to just speak up whenever we ask for questions, if they want to ask, or later on they can write in chat also. Yeah, Suhayan, please.
Right. Thanks for the nice talk.
Thank you.
You mentioned about this the criteria to check for non-classicality in states, so that we can say that okay, you can check if the states are entangled or not. So do you have any ideas how difficult is it to do the computation? Like, as in if I want to write an algorithm for it, or if the analytical methods that given a certain circuit, I just want to test.
Actually, for Agarwal-Tara, Up to 5 qubit, it is easier to calculate, and after that, more than 5, the dimension of the matrices becomes very high, and and the quantity is very high, so it is very difficult to calculate.
Right. Thank you. Yeah.
Okay. So we have PKP online. So please, sir, please.
Yeah,
ask a
see,
question.
Ramita, I just remember, see, this guy Patra gave a talk before your talk, right?
Yes, sir. Yes,
So
sir.
he found out multiparticle entanglement connected with topology.
I have seen.
And do you think there could be any connection of that with your, these n-body operators?
I think that can be done.
Think
It's
about it.
found.
It's just,
Yes, sir.
just
It's
think
found to
about
be
it.
interesting.
Yeah.
Yes, sir. I will check.
Yeah. Thank you.
Okay. Thanks. So let's